Hello and welcome back to Kuma English Listening Hub. Picture this. It's 6:30 on a winter evening in the UK. The kettle goes on in millions of kitchens. Ovens hum into life. The telly flickers in living rooms from Cornwall to Cumbria. And somewhere a teenager has just plugged in a laptop that's been on 1% for the last hour. None of this feels remarkable. You expect the lights to come on. You assume the power is simply there, like water in a tap. Yet behind that everyday certainty sits a system that is, frankly, a bit of a marvel. A national power grid that has to balance supply and demand every second of every day. Not every minute, every second. Because unlike tin beans in a cupboard, electricity can't really be stockpiled at the scale we use it, at least not cheaply and not for long. The grid is less a warehouse and more a tightrope walk. One wobble, and you can feel it across the whole country. Tonight, I want to take you inside that tightrope act, the secret choreography of the UK's power system. We'll look at why frequency matters, what happens when a power station trips, how wind farms complicate the picture, and why something as British as a cup of tea can genuinely move the needle on national demand. Along the way, we'll touch on control rooms, market rules, emergency reserves, and the quietly heroic engineers who keep it all sorted. Let's start with the basic problem. The electricity system has to match generation to consumption in real time. If demand rises, generation must rise. If demand falls, generation must fall. The grid's way of measuring whether things are in balance is frequency. In Britain, the target is 50 hertz. That number is not decorative. It's a sign that the whole system is spinning in sync. If there's too much demand and not enough supply, frequency dips. If there's too much supply and not enough demand, frequency rises. Either way, you don't want the deviation to get out of hand. Appliances and industrial equipment are designed with a certain tolerance, but push the system too far and you risk protective shutdowns. In plain terms, kit starts tripping off to protect itself, and that can snowball. So how do operators keep the frequency steady? First, through forecasting. The people running the system, in Britain that's National Grid Electricity System Operator, or NESO, are constantly predicting demand based on time of day of week, weather, and human behavior. The forecast isn't just a guess. It's built from decades of patterns, updated with live data. Cold snap? Demand rises. A major football match? It's not just the stadium lights, it's the halftime kettle surge at home. A bank holiday? Demand shifts in a slightly odd way because routines change. Then there's the supply side. Britain used to rely heavily on big, controllable power stations. Coal, gas, nuclear. You can tell them to turn up, and broadly they do, within technical limits. Coal plants were famously flexible in some respects, though not exactly clean. Gas plants can respond relatively quickly, and they've been the workhorses for balancing, though the country is increasingly keen on reducing reliance on fossil fuels. The modern mix is more varied. Offshore wind, onshore wind, solar, interconnectors to other countries, gas, nuclear, and a growing slice of batteries. That diversity is brilliant for cutting emissions, but it makes the balancing act trickier. Wind and solar are weather dependent. They don't take orders in the same way a gas turbine does. You can't ring up the North Sea and say, "Could you blow a bit harder, mate?" Because of that, the grid needs layers of control. Some responses happen automatically, in fractions of a second. Others are dispatched over minutes. Some are planned hours ahead. Think of it as having reflexes, then deliberate movements, then long-term planning. A key concept here is inertia. Traditional power stations with large spinning turbines provide inertia naturally. It's the same idea as a heavy flywheel. It resists sudden changes. If something goes wrong and a generator drops out, inertia helps prevent the frequency from collapsing too quickly, buying time for other responses. Renewables like wind and solar connect through power electronics rather than big spinning masses in the same way, so the system has less natural inertia. Engineers can create synthetic inertia using control systems and batteries, but it's different, more like a clever imitation than the real thing. Fair enough, It can work, but it has to be designed properly. Now, what does a typical disturbance look like? Imagine a large generator trips offline. Perhaps a fault is detected, perhaps an unexpected mechanical issue, perhaps a lightning strike causes protection systems to isolate equipment. Suddenly, supply drops. Frequency begins to fall. Within seconds, automatic responses kick in. Certain generators and batteries are contracted to provide frequency response. They inject power quickly or reduce output if frequency is too high. Some industrial users can also provide demand response, essentially agreeing to turn down or switch off for short periods. It's a bit like a dimmer switch on national demand, though the idea of a factory pausing operations for grid stability is, blimey, still surprising to many people. If that's not enough, the operator dispatches additional reserves. Gas plants can ramp up. Hydro, where available, can be very nimble. Batteries can discharge rapidly, though they don't last as long as traditional plants. Interconnectors can import more power from abroad if the market and physical constraints allow it. You might ask, why not just have loads of extra power running all the time, just in case? Because that would be wildly inefficient and expensive. Running spare plant constantly wastes fuel, raises bills, and increases emissions. The grid therefore relies on a carefully priced set of services. Some providers are paid to be ready, others are paid to act, and the whole system is shaped by market rules. Those market rules can get rather complicated. Electricity in the UK is traded ahead of time, sometimes days ahead, then adjusted closer to real time. Generators and suppliers submit plans, how much they intend to produce or consume. As reality diverges from plan, a balancing mechanism allows a system operator to buy or sell adjustments. It's a bit like planning a dinner party, then realizing at the last minute that your neighbor is bringing 3 extra guests and someone else has gone vegan. You scramble. You pay a premium for last-minute replacements. The grid does something similar, though with far more zeros and far less hummus. And then there's the famous British kettle effect. After a big TV moment, say the end of a popular program, millions of people make tea at once. That surge can be several gigawatts in minutes. The grid plans for it, with quick start reserve and frequency response. It's not folklore, it's a measurable pattern. You can almost hear the nation collectively thinking, right then, brew time. Let's move to another piece of the puzzle, voltage and reactive power. Frequency gets most of the headlines, but voltage stability matters too. Electricity isn't just about how much power is flowing, but how it's delivered across a network of lines and substations without going out of bounds. Certain equipment, like capacitors, reactors, and some generators, help regulate voltage. It's the less glamorous side of grid operation, but without it, you can't keep the system within safe operating limits. Now consider Britain's geography. A great deal of wind generation is offshore, or in Scotland, while a large chunk of demand is in England, especially the South and the Midlands. So you have power that often needs to travel long distances. Transmission lines have limits. If a corridor becomes congested, you can't just shove more electricity through it any more than you can fit 10 liters into a 5-liter jug. When the network is constrained, operators may have to constrain off generation in one place and constrain on elsewhere. In practice, that can mean paying a wind farm to reduce output because the grid can't carry it south while paying a gas plant near London to generate more. To the public, it can sound daft. Why pay wind farms not to produce? But the alternative could be overloads and instability. Over time, the solution is grid reinforcement, new lines, upgraded substations, smarter controls. Yet, building infrastructure is slow, politically fraught, and often met with local opposition. No one wants a pylon in their view, even if they want clean energy on the cheap. We should also talk about resilience and emergencies. The grid is built with redundancy, meaning that if one component fails, others can pick up the slack. That's why you'll hear phrases like N1 security. The system should withstand the loss of a single major element without causing widespread disruption. But sometimes failures cascade. A fault on one line pushes power onto another, which then overloads and trips, and so on. The operator's job is to prevent that domino effect. In extreme cases, controlled disconnections, known as load shedding, can protect the wider system. It's not something anyone wants to do, but it can be better than a complete blackout, which takes far longer to restore. If the worst happens and parts of the system go dark, restoration is a careful business. You can't simply flip the national switch back on. You need black start capability. Generators that can start without an external power supply. Historically, this might have involved certain hydro stations or diesel units. Today, batteries are increasingly part of black start services, though the engineering and procedures are understandably rigorous. All of this is happening while the energy transition accelerates. Electric vehicles add demand, but can also, potentially, provide flexibility if they charge at off-peak times or even feed power back into the grid. Heat pumps shift heating away from gas and towards electricity, changing winter demand profiles. Data centers and AI computing clusters can be significant loads. Meanwhile, more rooftop solar changes how power flows in neighborhood networks. Electricity can flow from homes outwards, not just from large plants inwards. That shift requires a more active distribution network. Historically, local grids were passive. Power came down from transmission, through substations, to consumers. Now, with local generation and batteries, distribution operators need better monitoring and control. Smart meters, automation, and dynamic tariffs all play a role. It's a bit like moving from a one-way street to a busy roundabout. The traffic patterns are more complex, and you need better signage. So, what should you take away from all this? First, the grid isn't a static machine. It's an ongoing negotiation between physics and economics. The laws of electricity don't care about politics, and the market doesn't care about your feelings. Operators sit in the middle, making real-time decisions to keep things safe and affordable. Second, the decarbonization journey is not just about building wind farms. It's about system services, inertia, frequency response, voltage control, reserves, and the ability to move power from where it's generated to where it's used. It's also about planning permission, supply chains, workforce skills, and public consent. In short, it's a national project, not a single technology. And finally, the next time you switch on the kettle, spare a thought for the people watching the numbers in a control room, ensuring that 50 hertz stays more or less spot on. You'll never meet most of them, and that's rather the point. When they do their job properly, nothing happens. The lights stay on, the telly keeps playing, the tea gets made, and the whole country carries on, none the wiser. Thanks for listening. If you enjoyed this deep dive into how Britain keeps the power system balanced in real time, stick around for more C2 level listening episodes here at Kuma English Listening Hub. Cheers, and see you in the next one.